Hello, this is Mr. Greisman, and in this vodcast we're going to learn about the observed trends in the periodic table. Let's first look at how the periodic table came about. First of all, the word periodic is not a random term that's used. It isn't just called the table of elements arranged randomly. Periodic is a very specific term. And it was a term that this scientist, Dmitry Mendeleev, a Russian scientist who in the middle 1800s observed that there were repeating trends in the properties of elements. The periodicity means that there are repeating patterns that resulted in him creating a table or organizing a table based on increasing atomic mass. Now, if we look at this table, you'll see that, and I'm just showing you a blank table, that it's a pretty specific set of squares. And all these squares represent a different element. You cannot take one square away. You can't add a square. The squares that are there have been placed specifically where they are because they exhibit these, quote, periodic trends. If you want to get more information about the periodic table and its discovery and the fascinating stories involved in the discovery of the different elements, this is a great book called The Disappearing Spoon. It's a recent book, very easy read. For those of you who are interested, I would highly recommend it. The modern periodic table is based on increasing atomic number and electron configuration. Now, electron configuration really just means the organization of the electrons around the nucleus. Periodic table is arranged into the following. This diagram is just a diagram of a periodic table, and you can see that the horizontal rows are called periods. So they would extend, horizontally. You can see the separation between the metals and the non-metals. Any kind of vertical column is called a group or a family. So groups are vertical, periods are horizontal. Now, this periodic table is not how Mendeleev envisioned it. This is the modern version of the periodic table. Regardless of the difference, there are numerous trends that are still observed, and we're going to go through each one of those individually. The trends that we notice in reactivity on the periodic table are, as we move down a group, so as we move down a vertical column, or as we move left to right in a period, the reactivity of metals decreases. Now, this is important that you realize here that we're talking about metals. We'll talk about non-metals in a second. So, as you can imagine, the element that probably is the most reactive is down in this bottom corner, and I'll let you determine which metal that might be. As we go across a period, so left to right across a period, reactivity decreases. Now with non-metals, this changes. So with non-metals, we're looking specifically at this part of the periodic table. With non-metals, as you move up a group or across a period, the reactivity of metal increases across a period left to right. So you would expect this element right up here, and I'm going to let you figure out what element that might be, would be the most reactive non-metal. Sometimes the trend in reactivity is described in this way. It's almost like an arrow going up that way and an arrow going down that way in terms of increasing reactivity. So, that's the first trend. Let's look at the second trend, and this is the trend in atomic radius. What is atomic radius? Well, it's not so easy to figure out what atomic radius is, but we can say the definition is that it's the distance from the nucleus to the most probable location of an atom's outermost electron. As we go down a group, atomic radius increases. So again, as you go down a group, okay, down a vertical column, whether you're talking about a metal or a non-metal, as you go down that group, the atomic radius increases. Now, the next term, though, is going to be counterintuitive, and what that means is that it isn't exactly what you would expect. As you go across a period, so as you go from left to right across a period, and this is regardless of metals or non-metals, the atomic radius tends to decrease. Which is, and when I say it's counterintuitive, because you would expect as we're going across the period that we're increasing the atomic number, we're increasing the number of protons, we're increasing the number of electrons, you would expect that the atom, or you would think that the atom would just get larger rather than getting smaller. Let's explain why these trends occur with atomic radius. There's increasing number of energy levels. So going across a period, we're staying at the same energy level, which means that the electrons that are being added to each element as we're building these elements and increasing the number of electrons, each of those electrons is being added at the same energy level. As we go down a group, that changes though. As we go down each group from 1 to 2 to 3, etc., we're increasing energy level each time. So if we have an electron way over here in group 18, and then we're adding one more electron to element 19, for example, potassium, potassium's atomic radius will be substantially larger because it's added that next or that outermost electron at another energy level. There was an increase in nuclear charge, and well, that means as you're increasing the number of protons, you're increasing the nuclear charge for that atom. And what happens is that each time you do that, all of the electrons are pulled closer and closer to the nucleus because that nuclear charge, that positive charge, is stronger and stronger, and the electrons are being added at the same energy level. And so what happens is that all of those electrons are being pulled closer and closer to the nucleus. And that helps explain why there is an increase in nuclear charge, and as a result, it causes the atomic radius to get smaller, going across a period. And the last effect is called the shielding effect. Now, the shielding effect, if you think about the levels or the energy levels of an electron, the inner electrons shield the nucleus from its attraction to the outermost electrons. And so if we're talking again about going down a group, as we're increasing the number of energy levels, what happens is that you are increasing what's called the shielding effect. The result of that is that the atomic radius would increase. So the trend in ionic radius is going to be similar to the trend in atomic radius. And when we're talking about an ion, we're either talking about increasing an electron and calling that an anion, or decreasing an electron and calling that a cation. Cation is positively charged, and you can remember that because CAT, T, is a positive sign, so you're creating a positive ion. Anion has an N in it, meaning a negative ion. The distance from the nucleus to the outermost electron of an element's respective ion refers to the ionic radius. So there are two trends, and this should be self-evident. A cation, that is a positive ion, would have a smaller ionic radius than their respective atom's atomic radius. So what does that mean? That means, let's say we have sodium, for example. Sodium has 11 electrons, 11 protons. If we remove one of the electrons, we therefore have one more proton than we have electrons, which means now that the 11 protons can exert a larger nuclear attraction for the 10 electrons, and all of those electrons are pulled closer to the nucleus, creating a smaller radius. Whereas the opposite is true with anions. They have larger atomic radii than their respective atom's atomic radius. If we think of chlorine, chlorine is element 17, 17 protons and 17 electrons. If we add an electron to chlorine, we therefore have 18 electrons and 17 protons. Those 17 protons can't exhibit the same nuclear attraction for those electrons, and so those electrons are able to move further away from the nucleus. Let's look at the next trend. That is the trend in ionization energy. Now, ionization energy refers to the amount of energy required to liberate or get rid of the outermost electron in an atom. Think of it this way. As our atomic radius gets smaller, the ionization energy is going to get larger. Why? Well, because as the atom gets smaller, it's able to hold all of its electrons more tightly. The result is that the amount of energy required to get rid of one of the electrons increases. The opposite should be true, that as atomic radius increases, the ionization energy would decrease. So that means that elements with large atomic radii, like these metals over here, large atomic radii, would not have a difficult time getting rid of their outermost electron and would have a low ionization. Would have a much higher element's ionization energy because their protons, the nucleus, is able to hold on to those electrons more closely and therefore make it more difficult to get rid of an electron. Let's look at the next trend. And that is the trend in electronegativity. Now, electronegativity is a concept that was developed by a very famous scientist, Linus Pauling, winner of 2 Nobel Prizes. Linus Pauling came up with this term to describe an atom's ability to attract an electron pair toward itself. So it's a number assigned to a bonded element outlining its relative ability to attract electrons. Now the key word here is relative, okay? And what does that mean? It's a relative term, meaning that there is one element that's considered to have the highest electronegativity, and then all other elements are considered relative to it. So if we look at the periodic table, we can generally say that the smaller the atom, the greater the electronegativity. And so if we look at fluorine right here, we see that fluorine has the highest electronegativity at 4, meaning that it's likely a very small atom, has a very high ionization energy, and would have a really high electronegativity. Whereas if we move over to francium, francium would be a very large atom, very low ionization energy, and a very low electronegativity. So if I can just demonstrate with my electron pair of science demonstration, if this is one new nucleus and this is another nucleus, and that's my electron pair, we can see that with these two hands being pulled equally, they're equidistant. The electron pair is equidistant between these two hands. But as soon as I have one hand or one element that's got a higher electronegativity, it's able to attract that electron pair closer to itself. We've just discussed the trends in the periodic table as a result of the work done by Mendeleev to create the periodic table. Thanks for watching.